Welcome back. In this video, we're going to take a look at a problem investigating two aspects of wave motion. The first is the Doppler effect, which causes apparent changes in frequency when detector and source are in relative motion to one another. The second aspect is the presence of standing waves in open tubes of air. Let's go ahead and take a look at the problem statement. In this problem, we have a scenario in which a tuning fork is struck right above this partially filled tube of water. The depth of the water must be chosen such that when this tuning fork at 440 Hertz is struck, it should set up a standing wave inside of this portion at the third harmonic, also at 440 Hertz. The first part of the question asks us to find out what is the necessary depth of water for that to occur. Now the second part of the question says, once you have a standing wave inside of here at 440 Hertz, we want to detect a frequency with this detector that's different than 440. We want it to detect a frequency that's not at the third harmonic, but at the first harmonic, so a lower frequency. For that to occur, the detector has to be moving, in which case the Doppler effect will cause a shift in the detected frequency versus the source frequency. Let's go ahead and solve the first part of the problem, which asks us to find the depth of water necessary to get the standing wave inside of here at the third harmonic. So what I'm going to do is go ahead and draw out a couple of possible standing waves inside of here. And we're going to use that to get a relationship between this distance, which is the distance between the top of the air tube and the water depth, and the wavelength of the standing wave inside. So what I'm going to do here is draw the tube, and I'll draw the water in the bottom here as well. What we're going to do is basically we're going to consider this as the air tube. There's not going to be any sound penetrating inside of here, or it's not relevant for our case. So we're going to consider this as basically this is the bottom of the air tube right here, and we want to find out what is the relationship between this distance and the wavelength of the standing wave inside of it for different harmonics. Now the key here is that air is oscillating inside of here, and it can only oscillate, it can't oscillate at the very bottom because it's at a boundary here. So there's no air particles over here oscillating, so this has to be a node. On the other hand, up here, you're going to have a lobe because you're going to have air particles oscillating with a free boundary. So we're going to have to draw a wave such that this part over here is at a lobe and down here is a node. There's a bunch of ways we can do this, but let's first start with the biggest wave we can do this possible, biggest wavelength possible. And that'll look like this. It'll look like something that has a node down here, it goes up to its first maximum here, and then if you continue drawing it up, it'll continue up like that. Okay. Now we can do the same thing by actually kind of similar to what I'd done in the string video, squashing this down by putting this lobe down here now. So we can actually squash the whole thing down. And based on these pictures we're going to draw in a moment, we can get a relationship between the wavelength of this wave and this distance right here, which is L minus D. What I'd like you guys to do is draw a couple more pictures of this for the next harmonics. This is the lowest harmonic because it has the highest wavelength. Go ahead and find out what the picture would look like for the next harmonic and the next one after that, and then we'll go back and using those, we'll find a relationship between the wavelength and L minus D. Take a minute to do that now, and we'll come back and take a look. So you should get some waves that look like the following. So what we're going to do in the second one is we're going to try to fit it such that the next lobe we see, which is right here, occurs at the top of the tube. So I'm going to basically squish this down, and that'll give this picture. And if you just continue it over. Okay, and then I'm going to do the same thing. Now I'm going to go from here to the next lobe and then put that one down to the top of the tube as well. So this one basically goes down like that. So the next picture looks like this. Now what we need to do is determine a relationship between this distance L minus D and the wavelength of each of these three different standing waves. In the first case, well, if we just kind of see how much of the wavelength is this, looks like a quarter of it. This is the full wavelength, and this is a quarter, 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 quarter. So a quarter wavelength equals L minus D for the first harmonic. What about the second case? In this case, we have, let's see, here's a quarter wavelength, one more quarter, and then one more quarter. So we have 3/4 of a wavelength equals L minus D. And then in this last case here, we have 1/4, 2, 3, 4, and 5/4. The pattern is obvious. Each harmonic occurs for an odd multiple of a quarter wavelength. In particular, the third harmonic, which by convention, when they say third harmonic, they don't mean the third in the series. They mean the harmonic in which case a 3 appears in the numerator. This is the third harmonic. That one is going to follow this formula. So if I write that down, I just have that this distance must equal 3 lambda divided by 4. Now, we're not given the wavelength of the wave. We're given its frequency instead. So let me use the fact that the frequency and the wavelength are related by the speed. Plugging that in here, you can trade out the wavelength for v over f, and you find that L minus D equals 3v over 4f. Solving that should give you the depth of the water necessary to make the third harmonic occur. We have L, we have v, which is the speed of sound in air, and we have the frequency, which is 440 hertz. So solving this for D, we find that D is 0.42 meters. Right? And that gives the answer to the first part of the problem, which was how deep does the water have to be such that this tuning fork at 440 hertz will cause the third harmonic to be set up here, the third standing wave. Now the second part of the problem says we don't want to detect a frequency of 440 hertz. We want to detect a frequency which is the first harmonic, which is the fundamental. So in other words, we want to detect a frequency which is actually much less than the 440 hertz. Well, first of all, what is that frequency? That frequency is, it's going to be, well, here's the frequency we're at right now. The fundamental is, of course, this divided by 3. So it's going to be 440 hertz divided by 3. So we want to detect, we call that frequency detected. We want that to be the fundamental, which is the third harmonic divided by 3, which is the third harmonic is 440 divided by 3, gives us 147 hertz. So we want to detect a frequency of 147 hertz. Now how do we do that? We're going to utilize a Doppler effect. The Doppler effect brings about changes in the detected frequency versus the source frequency. And that only occurs if the detector or source are moving relative to one another. In this case, the source is stationary. The tube here is not moving. But we can change the speed of the detector. So let's use the Doppler effect formula, which says that the detected frequency is related to the source frequency plus a factor. The speed of the wave plus or minus the speed of the detector divided by the speed of the wave plus or minus the speed of the source, all times the emitted frequency. All right, so the source frequency is 440 hertz. The detected frequency is 147. The speed of sound is 343. The source is not moving. The tube is not moving, so this term actually doesn't matter. And the only thing that's tricky about the Doppler effect problem is you have to figure out what the signs are. And there's a bunch of rules you can probably look up in your book, but I think the best way to do it is to just use a little bit of physical intuition. The intuition here is that, well, the detected frequency is always going to be less when the source and detector are moving further apart from one another. In this case, we want a source frequency less. So these guys have to be moving further apart. How do we make this less? We've got to make this as small as possible. To make this, because these are both positive, to make this numerator small, we want to use a negative sign. So we can get a smaller number in the numerator if we do v minus vd as opposed to v plus the vd. Plugging that in, we get the following formula. And here we know everything except for v sub d. 147, v is 343, and the source is 440. So you can solve to get that the detected speed has to be 228 meters per second. Right? So it actually has to be moving up at quite a fast speed to detect a frequency that is much less than the emitted frequency. All right, and so that's it for this problem. The first part of the problem asks us to find out what is the depth of the water needed to set up the third harmonic inside of this air tube. And the second part of the problem asks us to find out what is the detector speed needed to detect a frequency that's 1/3 of the source frequency. I'll stop there. If you have any further questions, go back and look at the write-up and then the summary on the next slide, and I'll see you next time.